These are notes on predicting single and double displacement reactions. So if you remember at the beginning of the unit, I said this is kind of where we're heading to figure out A, if a reaction will happen when two substances are combined or put together, and then B, if a reaction will happen, what the products are going to be. So we're going to look specifically at single and double displacement reactions, and then we're also going to look at something called net ionic reactions. And this is going to be chapters 11.2 and 11.3 in your book. So, single displacement reactions. As we've talked about, a more active element will replace a less active element. So, if we think about activity as in how attractive an element is, remember the more attractive elements are going to replace less attractive elements. So you can think of reactive and attractive, kind of sounds similar. And you can use something called an activity series. So you can actually download that on my website if you haven't already found it in the book or online. And I'll show you where that is and what it looks like. Let me end this for a second and come over to here. So you can download this. These are solubility rules, and we're going to talk about those in a little bit. But then down here we have the activity series. So here are metals. And the more active metals are at the top, the less active metals are at the bottom. And then the same with nonmetals. The more active metals are at the top, the less active ones are at the bottom. So things that are kind of up here are more attractive than things down here, and so they will replace things that are down there. So again, if you think of this as, like dating or going to prom, if we want to make it really dramatic, then we would say that sodium is more attractive than zinc. So if zinc shows up with somebody, say a nitrate, zinc nitrate, and then you have sodium show up, sodium is going to replace zinc because sodium is more attractive. However, if zinc nitrate's hanging out, zinc and nitrate are hanging out, and tin shows up, tin is not going to replace zinc because tin's not as attractive. So why would nitrate ditch zinc for tin? So these guys down here, less attractive. These guys up here, more attractive. All right. Okay, so substances, as we said, higher in the table will replace substances lower in the table. Okay? So what I want you to do now is here are 4 single replacement or displacement reactions. I want you to figure out which ones will occur, like which ones will have a reaction and which ones will not have a reaction. Okay? So what I would do is pause the video, take a look at your reactivity series, and figure out which ones will and which ones will not. And if they will, what will they form? Make the balanced equation. So go ahead, pause the video, take some time, figure that out, and then you can start the video and check your answers. So you should have found that magnesium will replace the hydrogen in hydrogen chloride or hydrochloric acid. So if we take a look at our reactivity series, let's go ahead and get that. So if we're looking, here's magnesium up here. Here's hydrogen down there. So magnesium is definitely more reactive than hydrogen, definitely more attractive. So if hydrogen shows up with chlorine, and then here comes magnesium, magnesium is way more attractive than hydrogen, definitely going to replace it. And so the magnesium then has replaced the hydrogen. And here we can even get our little pen going on here. Let's get our pen. So the magnesium replaces the hydrogen. The hydrogen then ends up single, which is another way you can remember it's a single replacement reaction. Somebody said, oh, then the hydrogen is single. And you get your magnesium chloride and your hydrogen gas. Now, one thing that's important to note is notice that magnesium in an ionic compound forms a 2+, chlorine forms a 1-. So that's why we have 2 chlorines to 1 magnesium. And then you also have to remember hydrogen isn't going to exist all by itself as an element. That's going to form a diatomic gas, so it's going to be H2. And so that's really important when you're making these reactions to do it properly. And that's actually why I had the 2 HCl here for that, because then it's nicely balanced. So then the second reaction also occurs. So if you, again, go back and look at your reactivity chart, the aluminum is above the zinc, making aluminum more attractive or more reactive. So the aluminum is going to replace the zinc, and the zinc ends up all by its lonesome self, single replacement. And again, here you have to figure out aluminum forms a 3+ charge, and chlorine forms a 1-, so you end up with 3 chlorines to 1 aluminum, and then zinc, it is a solid metal, so that's just zinc, and then you can balance it out. So this goes back, when you're predicting the reactions, it's really important to remember to check the charges on ionic compounds, or to check the Lewis structures on covalent molecules to make sure you're getting the right ratio of elements in a compound so that you can balance effectively. Then we look at aluminum and sodium chloride. So let's take a look at our reactivity series again. So in this case, we notice that aluminum is down here and sodium is up here. Sodium is more attractive than aluminum, so chlorine's going to stay with sodium. It's not going to ditch sodium, something that's way cooler than aluminum, for something that's less attractive. That would be silly. So in this case, we see that there's no reaction. And then again, sodium is way higher up on the reactivity series than hydrogen. So chlorine is way happier with sodium than with hydrogen, because sodium is a lot more attractive. So here again, we're going to find that there's no reaction. There are more of these in your book, so you can practice those if you want more, and we'll practice some more in class. So let's look now at double displacement reactions. So now we can look at double displacement reactions. I may have just said that, but I had to pause for passing time because there were bells ringing. So double displacement reactions do not occur. So we're looking at when that in general they do not occur unless, so these are the conditions under which they do occur. The reactants are dissolved in water so that the compounds can separate into ions. So remember, the whole reason that ionic compounds conduct electricity in water is because their ions separate and they're kind of flowing around. If that doesn't happen, you're not going to get a double displacement reaction. So even if 2 compounds react when they're aqueous, they're not going to react when they're solid. So just keep that in mind. In order to get a double displacement reaction, the reactants must be dissolved in water so that the compounds can separate into their ions. Ionic bonds are really strong. They're the strongest of the bonds, and so they're not likely just to separate and go their own way. So you need the reactants dissolved in water, but you also need one of these. Okay, you don't need more than one, just one is good. You need one of the products to be a gas, one of the products to be a precipitate. So when we say a precipitate, we're talking about a solid, or having water as a product. So numbers 1 and 3 are pretty easy. One product is a gas, water is a product, we get that. One of the products is a precipitate means that when you mix these 2 substances together as aqueous solutions, one of the products stops being aqueous. It doesn't dissolve in water, so you get a solid. And what that often looks like at first is simply a cloudy or colored water. But then if you wait long enough, whatever solid that is falls to the bottom. It's generally more dense than water, and so falls to the bottom. You may remember earlier in the year there was a beaker of like weird red stuff in our room for a really long time that AP was looking at. They were looking at precipitates. So some of you noticed that if you stirred that, the water got all red and cloudy, but if you waited long enough, the red stuff, it was some kind of iron precipitate, fell to the bottom, and then the water on top was clear. So that would be a precipitate. And then you can use a solubility table, which we'll look at in a second, which shows the solubilities of various ionic substances in water. They're really like solubility rules, and that can help us determine or figure out if a precipitate is formed. So let's take a look back at that table that we've been looking at for the reactivity, but in this case, let's look at the solubility rules on them. So these are ions that form soluble compounds, and then we have exceptions, and then ions that form insoluble compounds, meaning they don't dissolve, and then exceptions to that. So this is kind of the reverse idea of this. So any group 1 ions, lithium, sodium, anything that's an alkali metal, if it's bonded to an alkali metal, it will always be soluble in water. Okay? There are no exceptions to that. The same with, say, nitrates. Nitrates are always soluble in water. There are no exceptions to that. But then you get halides. Halides, the halogens, right? Bromide, chloride, iodide, fluoride, etc. Halides are generally soluble. Their exceptions are if you have silver, lead, or mercury. Then those are not soluble in water. Okay, so aluminum chloride would be soluble in water, but silver chloride would not. You can read through the rest of these. It's important that you know how to use this table, but you don't need to memorize it. I will give you this table when you need it. I would print it out so that you have it in class to use, but again, you don't need to memorize it. Then on this side, these are insoluble. So in other words, carbonates are always insoluble, except when they're combined with group 1 ions or ammonium. So notice these are all positive ions, carbonate is negative. So if carbonate is combined to a group 1 ion, like sodium, then it will be soluble because group 1 ions are always soluble. And it just has to do with the different properties that these compounds have. Sulfides, for example, are never soluble. So they'll always precipitate out, again, except when combined with these ions, these positive ions that are always soluble. And again, you can kind of read through what these are and know how to use it. So now let's go ahead and figure out how to use it. So here we have a list of 4 double displacement reactions. And I specifically have not put in any states of matter simply because if I did that, it would give it away really easily. But I want you to pause the video, use your solubility rules, and figure out which of these reactions happen and which of these reactions do not happen. So go ahead and pause it and then figure that out. All right, so equation number 1 would actually happen. So because the chlorides are always soluble except when they're bonded to silver. So this here would be a solid. So essentially you would mix these 2 solutions and you would end up getting silver chloride, which is solid, and then sodium nitrate, which is soluble in water. So that would be aqueous. That would be dissolved. So it would look like kind of clear water with foggy silver chloride in it. And these, the silver nitrate, the sodium chloride, and the sodium nitrate would all be aqueous because they're aqueous solutions. So then this second equation would also happen because while the potassium here, potassium's a group 1, so potassium nitrate is going to be soluble in water. It'll be aqueous, and nitrates are always aqueous as well. However, aluminum hydroxide, hydroxides, if we go and take a look at our chart, hydroxides are, well, let's actually do that. Let's take a look at the chart first. So we've got hydroxides. Hydroxides are never soluble except when combined with our group 1 ions and ammonium and some group 2 ions. So those, if you look at a periodic table, to make life a little easier, you might notice that those are all alkaline earth metals. But in our example, the aluminum, it was aluminum bonded to the hydroxide. So if we come back over here, it's the aluminum bonded to the hydroxide, so that is insoluble. So that ends up being solid. And so we get this dissolved potassium nitrate and solid aluminum hydroxide. So that will happen. And then again, everything else is aqueous. So here we've got NaOH plus HCl. Here we have NaCl and water. Remember, if you go back to the rules from the previous slide, one of the things we were looking for was water. If one of our products is water, then that is a reaction. So this is liquid water, so we put our L there. This again is aqueous, and so that reaction happens. So then we have our final reaction. This reaction does not happen because we've got alkali metal here and alkali metal there. That's really all we need to look at. Nitrates are always soluble as well. Bromides are usually soluble, except when bonded to a couple of things like silver. But it's bonded to an alkali metal, so we know that these are all soluble in water. So this reaction actually doesn't happen. And the reason for this is I want you to think about what happens when you mix potassium bromide, and sodium nitrate together when they're aqueous, right? These are both aqueous, meaning they're dissolved in water. So if you have a beaker, let's kind of get a beaker here, and you've got aqueous potassium bromide, you've got your potassium ions, and you've got your bromine ions, and I'm just going to do one to make it easy, and I'm also not going to include the water, again, just to make it easy, but this would be a beaker full of water. Here we can do that to symbolically represent water. And then you put in your aqueous sodium nitrate, so you get your sodium ions, and you get your nitrate ions. And then because these, potassium nitrate and sodium bromide, are also soluble in water, you get exactly the same thing. Just all these positive and negative ions floating around. There's no reaction. It's no different here compared to here. Here it's different because you get this liquid water. Here it's different because you get a solid aluminum hydroxide. Here you get a solid silver chloride. But here you get a beaker with a bunch of ions floating around, and here you get the same beaker with a bunch of the same ions floating around. No reaction actually happens. So now I want to look at net ionic equations, which is 11.3. And this is going to take this idea of what's going on with the double displacement reactions and what's actually happening. So let's take that first reaction that we had, and now I've got our states of matter in here. So it was aqueous silver nitrate plus aqueous sodium chloride yields solid silver chloride plus aqueous sodium nitrate. And what we're going to do is we're going to divide these up into their ions. So this is what's called a complete ionic equation. So it's aqueous silver 1 plus ion plus aqueous nitrate ion. And we know the silver is 1 plus because we know nitrate is 1 minus. Here's our sodium ion and our chlorine ion, and that yields silver chloride, which is solid, so it's not aqueous, we're not going to break it up into ions, it's a solid product, plus aqueous sodium ion and aqueous nitrate ion. Now what we're going to do is we're going to cancel out anything that appears identically on either side of the yield sign in the reactants and the products. So we've got a sodium ion here and a sodium ion there. We've got a nitrate ion there, and a nitrate ion there. And those are called spectator ions. They don't actually participate in the reaction. And what we're left with is the silver ion, the chlorine ion, and the solid silver chloride. And so then we can write what is called so then we get what's called our net ionic equation, which is just the parts that participate in the reaction. So we get the Ag plus Cl minus yields AgCl, or silver ion plus chlorine ion yields silver chloride. All right, let's now look at how you would balance the net ionic equations. It's pretty similar to how you would balance any regular equation with one minor difference, and so I'll show you what that is. So when we balance net ionic equations, the atoms of each type need to be balanced, which is what we've been doing, and the charge needs to be balanced. So you need to have the same charge on the reactant side as on the product side. So let me show you an example of that. So let's look at this equation. Solid lead, so this is a single displacement reaction. Solid lead is added to silver nitrate, and we get solid silver and lead nitrate. And so here, the lead is going to replace the silver. If you go and look, you'll notice that lead is higher on the activity series than silver is, so lead easily replaces the silver. And so this then is our complete ionic equation. We get our solid lead, plus we have silver 1 plus and nitrate 1 minus. Again, we know that from the nitrate, and those are both aqueous. And that gives us solid silver plus lead 2 plus NO3 nitrate 1 minus. And again, we know that because here in our equation we have 2 nitrates, so that's going to be a total 2 minus charge, giving our lead a 2 plus charge. So then we can go through and say, okay, what are our spectator ions? What's similar on both sides? So we can cancel out our nitrate, and that's it. We can't cancel out the silver or the lead, because if you notice, here the lead is solid, here it's a lead ion, it's aqueous, and so that's not the same. So the only thing that's the spectator ion is the nitrate. So then we do our net ionic equation. So we have solid lead plus aqueous silver ion yields solid silver plus aqueous lead ion. So first, let's balance out. Now, if you just look at atoms of each type, you'll notice that's balanced. We have one lead, one silver, but the charge is not balanced. Here our charge is a 2 plus, here our charge is a 1 plus. So we need another silver ion, so I'm going to kind of squeeze a 2 in here, in order to balance that charge. Now we have 2 pluses, which gives us a 2 plus charge, and that balances out our 2 plus here. But now our atoms of each type aren't balanced. We have 2 silvers and only 1 here, so we need to put a 2 in there, and now that's balanced. So it's solid lead plus 2 silver 1 plus ions, which are aqueous, yields 2 solid silver atoms plus 1 lead 2 plus aqueous ion. So again, there are more of those in your book, and we'll practice those in class. Please make sure to add any questions you have to the comment section, or if you're doing this in class, please pause the video and ask. Have a good day.